working. Okay, today we're going to do a couple more review topics, starting out with finding the average atomic mass of different isotopes. This is a pretty easy method. Y'all have done it a ton of times in Chem 1. And ultimately, it's a weighted average, taking all the different isotope masses, multiplying them by their percent abundance in nature, adding them up, and getting the average atomic mass. So in number 20, here they have 3 isotopes, neon 20, 21, and 22. And they have the atomic masses of each individual isotope, each individual one. What does that U stand for? It's actually supposed to be like more of a mu. Anyone know? An AMU, yeah, an atomic mass unit, an AMU. Which, if you convert, you can convert that to kilograms through a number or something to the negative 27th. I can't remember it exactly, but once you start getting into physics, you will know that number. It's also the same number that we would use in grams per mole, but we're only looking at one individual nucleus right now, so it's one. That is the AMU measurement for that nucleus. Now here's a question I have for you. Anyone can tell me why this number is a decimal? This is a nucleus with neon, and neon has 10 protons, and in the first isotope case should have 10 neutrons. So if a neutron weighs 1 AMU and a proton weighs 1 AMU, why is the weight of the nucleus 19.992 instead of 20? Anyone know? What now? No, and I heard someone say average. We're finding the average. We're looking for the number right there. We're looking for the atomic average. So it has nothing to do with the fact that's an average. This is the mass of that one nucleus. Any ideas? Y'all did a calculation for this. I know you did. Tell me about what's in the nucleus. What's in the nucleus of an atom? Protons and neutrons. Tell me about protons. They're positively charged. Okay. So you're shoving all these protons into a really small area. No problems with that? Right. Don't like charges repel? Huh. So how are they staying together? How are they staying together? Y'all did this. Boy, look at all the blank faces. Some of the mass, the missing mass, is converted into energy that holds the nucleus together. What's that energy called? Binding energy. Okay? Does that ring any bells now that we've said it? Okay. So we're not calculating binding energy yet. We will. But I just wanted to point out to you why that makes these decimals and not whole numbers. Okay? So let's get back to the actual problem. This problem now, we need to find the average atomic mass of all 3 isotopes. So to do that, it's just like when you calculate your grades. You take the number that goes with each category. So in this case, our first one is 19.992 AMUs. And we're going to multiply it by the percent in decimal form. Then what do? We add it, good, to the next one. 20.994 AMU isotope exists. 2.57%. Be careful, make sure you change it correctly. It's 0.0257. And then we're going to add it to our next one, 21.991 times 0.0882. So let's go ahead and give me the same number of decimal places as in the table there as in all the other ones we're using. And say it loud and proud because I'm deaf. And I found out that I'm blind. I now have to wear glasses when I drive. I'm very, very depressed about that. So kind of failed the eye test. I know. I've never worn glasses. I kind of have to just get over it. All right. What is it? Anybody? 20.65. Can I get a second on that? I always want to make sure the number we put on the video is correct. Great. All right. 20.656. That number makes sense to me because this is such a high percent. You would think that it would be close somewhere. It would have to fall somewhere within there, okay? Because that 90% is most of the isotopes. All right, questions on that? Okay, we're going to do another one of these. We're just going to approach it a little bit differently. In this one, the problem's saying there are two isotopes of chlorine. One of them is Cl35, and it exists 75.77% of the time, and it has a mass of 34.96885. The question says, oh, well, what's the other isotope of chlorine? So we don't know the other isotope of chlorine, and we're looking for its atomic mass. Huh. There's only two isotopes, so can anyone at least tell me what the percent of that one is? 24.23. How'd you figure that out? Subtract from 100. If you know there's only two isotopes, both of those have to make up 100% of the isotopes, so you subtract. Now, I apparently must know another piece of information. When I set this up before, like I did on the last page, my job was to calculate the average atomic mass. Well, they apparently think we already know that. Where might we get the average atomic mass? Periodic table. The average atomic mass is 35.453. So that's going to be what we set our whole thing equal to, our whole statement. So 35.453 is equal to, so we know our first isotope weighs 34.96885, and its percentage 0.7577. Oh, there goes the strange dyslexia brain of mine. 7577 plus, I know the percent, right? I know my percent is 0.2423. What do I do for the mass? X. So I'm going to solve for that. So just give me I like to try to keep consistency in these kinds of problems, so I know it's a lot. Just give me 5 decimal places. 36.96699. So if I were to do a little thing like this and have a nice, clean, rounded mass number, what would I write? Yeah, Cl37. And that is correct. Okay? Yes? As long as you show your steps and the AP graders can follow your logic, they will give you full credit. Okay. Now, there's one other type of problem which is in your homework that I'm not going to do an example of, but I'll talk about how to do it. Another type of problem that you're going to run into is where you're given the two isotope AMUs. So you're giving the two isotope AMU masses. You're given the average atomic mass, and you're told to find the percents. You're not given either of the percents. That's another type of problem. Any ideas of how we would do that? Yes, no. Good. X would be one of them, but since we're not in percent, we're in decimals, what's 100% in a decimal form? 1. Right. So what we're going to do is you're going to have your average atomic mass. You're going to set that equal to the first percent, you don't know what it is, times whatever the AMUs of that first isotope is, plus 1 minus that, right? Because doesn't both of them together added up equal to 1, which is 100%, right? Times the AMU of the other isotope. And again, you're going to have to do your homework to experience these problems. I think one in your homework is actually 3 isotopes, but they give you one of them. So with that information, you can kind of do the same thing. All right. Another thing to be really careful of, keep track whatever isotope you set x equal to or times versus which one you did 1 minus x. Make sure you keep note of which is which, because when you report it, you have to report it correctly. Got it? All right, so that's all on average atomic mass with different isotopes. So now we're going to move on to percent composition. This is so easy, folks. When you took Algebra 1, what was the baby formula for percent? What do you say to yourself? Percent is part over whole, and that's all this is. This is percent by mass. So in this particular case, the question says, determine the percent composition of each element. Majority of the time, they're only going to ask you for the percentage of one element, but just for practice sake, we are going to find the percent of all the elements in this. So what would be the whole mass of this? How would we find it? Periodic table. We need the molar mass, so go ahead and solve. 366.01 grams per mole. All right, so there's our total. Now I'm going to I like doing things in charts just because that's how I roll. So I'm going to start with percentage of nickel. I need to be sure to include all of the nickel, not just one, right? So it would be 3 nickels. So 3 times 58.69 is what? 176 point what? 0.1? Part over the whole of 366.01. Is that right or wrong? I don't know why y'all were laughing. I thought maybe you were laughing because I wrote something down incorrect. 366.01. All right, grams, part over whole. How do I make this a percent? Times 100. All right, so what's my nickel percentage? And I'm not going to freak about sig figs on this kind of problem. I really don't have the energy. All right, percentage of P. So how many P's do we have in that formula? 2. So 2 times 30.97. Part over whole. Again, times 100. Okay. Now, a fast way to figure out the last one would be just to subtract from 100, but we're not going to do that. We're going to use the 100 as a check. We're going to find them all and then add them up and make sure we get 100. So my last is my percentage of O. How many O's are in this equation? 8. So we go 8 times 16, 128.00, divided by whole times 100. And so we get, all right, it won't be exact due to rounding issues, but when we add these up, we should get pretty darn close to 100. So this would be a good way to check your work to make sure. If you're off, really off, there's a mistake somewhere. You guys got exactly 100. Nice. I guess you are skilled rounders. Last period didn't get it. They got 99.998. They seemed a little bit upset about that. So I'm glad y'all are okay with this. That works. Do you have a question or you're just stretching? Oh, fist pumping. Go Jersey Shore. All right. So those are percent comp. That's all I'm going to spend on that. That's Algebra 1. That's easy stuff. What I want to really talk about are these really, really awesome empirical and molecular formulas. We spent a lot of time on this in Chem 1. It's a really, really important topic. There are about 8 billion different ways you can collect information to give you the information you need to get to this point and actually find empirical molecular formulas. This is one of those things that's going to continue to show up all year long. What's different in AP is how do we get that percent, that 26.6, that 35.1, where does that come from? And that's what we'll expand on. But what we're doing right now is just reviewing how to find an empirical formula and then a molecular formula. First off, what is an empirical formula versus a molecular formula? Who wants to speak? Go ahead. Which one? The empirical formula is the basic ratio, okay, of one element to another. It's the lowest whole number ratio, okay. What is the molecular formula? How it occurs in nature. Can a molecular formula and the empirical formula be the same? Absolutely, okay. Can you give me an example of that? Okay, well, they're not in compounds, and when we talk about formulas, we mean multiple elements. Okay, and it's okay because that's, again, that ionic business with the lattice kind of like breaks that theory. How about something even easier than that? Carbon dioxide. What? I don't know. My brain always goes to water. I don't know why y'all don't go to water. Water, carbon dioxide, you know, all of those are how they exist in nature, and they're empirical formulas. But what about like glucose? What's the formula for glucose? C6H12O6. That's how it exists. That's how glucose exists. But is that its empirical formula? No. What would the empirical formula for that be? CH2O. Okay. Does anyone know what type of compound, if you were on a diet and you were counting different things of the diet, what glucose would? Is it a protein? Is it a fat? What is it? Glucose. Just a carbohydrate, right? Huh. Carbohydrate. It's pretty cool, huh? All carbohydrates have that empirical formula. See? Can't say you didn't learn anything in chemistry. All right. So anyway, that is what an empirical versus molecular formula is. So in this particular problem, they're giving us some information. They're asking us to first find the empirical formula, and then they give us some additional information. Then they say the compound has a molecular weight of that. The molecular weight is always the weight of the molecular formula. Okay? When they give you a mass, that's how it exists in nature. So that's something we're going to address in a minute. But the first thing I would like to do is show you how to find the empirical formula. Again, I'm a big table freak. So I'm going to start with potassium, and then I'm going to go chromium. Word to the wise, don't be rearranging these things. It seems like every year there's one person who decides they don't like the order that the problem lists those percents in, and they start changing them up just because they feel better the way I don't know. Leave them in the order they give them to you in the problem, no matter what, because that's the order they're going to be in the compound. Okay? All right. So under potassium, we see that 26.6% of our compound is actually potassium, 35.4% is chromium, and 38.1% is our oxygen. Now, when we're finding our formula, we need those subscripts, and those are actually not ratio, they're ratio of atoms, but before we can even get to particle city, we always have to be in what? Moles. So we're actually going to find a mole ratio, which is actually the same as the ratio of atoms. Why? Because 1 mole is always 6.02 times 10 to the 23rd atoms, right? So we're cutting the problem shorter by stopping at moles. It makes it easier on us. We don't have to go all the way to particle city and do it, because that would just be extra work with really big numbers for no reason. So we need to convert to moles. But I don't have anything I can use to convert to moles. I have percent. So what can I do? But to get from molecular weight to moles, don't I need grams? Okay, so what do? That's it. Pretend I have 100 grams of the substance. If I have 100 grams of the substance, I'm utilizing these ratios. These are the ratios of those compounds under the assumption I have 100 grams. So all I have to do is pretend these are grams. Some problems, they'll give you grams straight up, and they won't add up to 100, but they'll just give you grams. Don't try to make it fancy and do something weird. That's already easier on you than this. This, you are actually assuming you have 100 grams, and you're converting percent to grams. All right? So now we're in grams. Like we said earlier, we got to get to moles. So how do I convert to moles? What do I do with the molar mass? Do I multiply? For every 1 mole I have for potassium, bam, 39.10. I'm going to write this first one down here. I guess this is going to be ugly on the video. It's not going to be very spread out. I should have made my chart a lot bigger. And then what about, so here my grams cancel, leaving me in moles. Chromium is 51.10, or 52, whoa. 52.00. 52.00 grams. And then here, for every 1 mole, I have 16.00 grams. All right, so what I want you to do when you're doing these empirical formulas, don't round at this point. There's no point in rounding. Give me 4 or 5 or so decimal places here. So start with the potassium. What do we get for moles? Okay, chromium. Okay, and then oxygen. All right, those are all my moles. So now I need to find the lowest number mole ratio, whole number ratio. What do I do next? Divide all of them by the lowest number of moles, 0.6803. Okay, this is going to be 1. I can tell that's going to be really, really, really close to 1. 1.00, what, how many O's? Just want to show you how close to 1 it is. Yeah, that's 1. And this one, I don't know. I don't know what that half means in chemistry. I don't know. Thank you. Okay. So if I were to stop here, I'd say my formula is KCrO 3.5. But my problem is empirical formula by definition is the lowest whole number ratio. So what do I need to do? K2 Cr2O7. Beautiful. Now, does this formula make sense based on what you know about nomenclature and all that kind of jazz? Yeah, what's that called? Good, potassium dichromate. This is, we know because we just calculated, is the empirical formula. Our job is to find the molecular formula. We know the molecular formula has a mass of 294.2 grams per mole. So how are we going to find the molecular formula now? Correct. Find the mass of the empirical formula and see if what even number multiple would be required to get the empirical formula mass to become the molecular formula mass. So what is my mass of my empirical formula? When you add this up on the table, you get 294.2. How convenient. What does that mean? The empirical formula is the same as the molecular formula. So our molecular formula is K2 Cr2O7. Now that's not always going to be the case. This is where you have to do your homework to see all the different kinds of problems and scenarios you run into. If you ended up with 147-ish as an answer here, let's say your empirical formula weighed 147. That empirical formula mass is always going to be an even multiple of the molecular formula mass if you did the problem correctly. If it's 147, what would you have to do then? Multiply the empirical formula by 2 in order to get to the molecular formula. Okay? And that's just a beautiful thing. Knowing it's going to be an even multiple, that's your check. If it's not dividing and you're not getting a nice, clean, whole number upon the division, you messed up somewhere. And so you go back and find out where your problem is. It's pretty much giving you the answer. That is if you pay attention to that kind of thing, okay? All right. I'm not going to do this on video, but in a minute I'm going to show you a really, really sexy way to do this on your calculator. It's kind of the best thing since sliced bread. But before I turn the video off, I just want to do one more problem to give you a taste into stoichiometry, which we're going to be getting into more on Friday. I'm going to take you through this really easy one-step problem first. We're only going to do 24. It says determine the amount of iodine produced. So since that's a solid, we're looking for how many grams of iodine are produced when 145 grams of Ki react with excess copper 2 chloride. Why did I write all that down? My goal when you're reading these problems is for you not to have to go back and read the problem again. By writing down what I did, you know that potassium iodide has a certain number of grams that you're starting with. You know that copper 2 chloride's in excess, and you know what you're looking for. You never have to go back and look at that problem again. In order for us to solve this, we have to do stoichiometry. We're going to have to go from here to there. The term that I use for this is called mole bridge. I need to mole bridge over. Okay? I need to physically cross this little bridge to get to iodine. But to be on the mole bridge, I need to be in moles. That's why I call it the mole bridge. So I can't cross that bridge until I am in moles. I'm going to start with my given, 145 grams of Ki. Now I can't cross the bridge until I'm in moles. So for every 1 mole of Ki I have, molar mass of Ki is 126.90 plus 39.10, 0.00 grams of Ki. When you're doing stoichiometry, because we're going from one thing to another, it's kind of crucial that you write your units of what, not just the units, because we need to know whether we're in Ki or whether we're in I units. All right, now we're in moles of Ki, so now we can cross the mole bridge. The mole bridge has guards on each side of the bridge. It's got a guard here and a guard here, and those guards are based on the stoichiometric coefficient in the balanced equation. So the relationship between Ki and I2 is 4 moles of Ki for every 1 mole of I2. That has brought me to this side of the bridge. Now I'm not done because I'm in moles and the problem's asking for grams. So how do I get from moles of I2 to grams of I2? Formula mass. I have 126.90 times 2. Point what? 0.8 grams. So moles of I2 cancel. So to 3 sig figs based on the original number of sig figs in this problem, how many grams of I2? 55.4 grams of I2. So that's the mole bridge. And we're going to be working on Friday. I'm going to show you these problems which are a little more complex in that, like here it says, determine the moles of CO2. We're going to look for moles of this and H2O formed of this as well when 2 moles of this are reacting with 10 moles of that. Can anyone see the difference between the problem we just did and this one? What is the difference? What did you say? Well, this is kind of multi-step to me. What did this X tell me up here? That means excess. What did that mean about that Ki? If potassium, it was all used up. What was the thing called that was all used up? The limiting reagent. So in a case like this, we got to figure out which one's going to run out first, which one's the limiting reagent. And once we do, we will then mole bridge over to the products. Okay? So that's what you're learning on Friday. You're relearning limiting reagents, and then we're going to talk about percent yield. So if you want to get a jump on it, Friday's a long time to go without doing any chemistry. Work ahead. See if you can remember how to do limiting reagent problems. Okay? All right, that's it.